Okay, here we go. Welcome to lesson 6.6 notes, solving exponential and logarithmic equations. So it's split exactly like that. We'll do the first half. We'll talk about, it's very brief as far as note-wise goes. It's solving equations. First part is exponential, where we have an unknown, a variable as an exponent or as part of an exponent. And then the second part is solving an equation involving logarithms. So here we go. First thing, exponential. So get a section set up, exponential equations. There's, kind of a simpler version. Basically, if we have the same base, this is a perfect example right here. If we have the same base, 3 to some power is equal to 3 to some power, the only way that this could ever be true is if those exponents were the same. And I know, like, obviously we can look at this and say, oh, of course, xx has to equal 5. Well, that could be potentially more complicated, a problem like 5 to the 2x plus 3 power has to be equal to 5 to the negative x minus 9 power, something like that. Well, it's the same property, though. This exponent the only way that this could ever be true is if those two exponents were equal. So that's the first part, or first type of problem we'll see when we have the same base. We're going to equate or set equal their exponents. Okay. Now that's limited because what if we don't have the same base, or what if there's not a power over here? So we'll have a few different techniques that we'll use, but I think the big takeaway or the big reveal here is that taking the log of both sides of the equation is kind of like a new tool for our toolbox, right? I think hopefully we all know when we're solving equations, it's okay to add 5 to both sides, or it's okay to square root both sides, or to square both sides of an equation and still be equivalent. Well, kind of the new part is it's okay for us to take the log of both sides of an equation, and we'll see that there's advantages to doing that, okay? So let's kind of work through a couple examples. I think they get kind of progressively harder as we go. We won't see any like this, at least during the example, because I'm assuming we could all solve that equation, 2x plus 3 equals negative x minus 9. Let's kind of take it up a level from there. All right, so here we go. Solve. It gives us a little hint there, solve by equating the exponents. But basically it's saying, hey, solve this equation. Tell me what x is. 64 to the x power is equal to 16 to that same x plus 1. So when at first glance, it's hopefully very wow, those aren't the same base, but there is a relationship there. Like 16 and 64, at least to me, kind of stand out as those are there's a connection there, I feel like. So here's what I would do if I just start listing. I'm basically looking for different ways to write 64, and not 32 times 2, but something to a power. So a really obvious one hopefully is 8 squared, right? That's just a different way to write 64. What's another way? Let's see, 4 to the third power. 4 times 4 times 4. And actually, so is 2 times 2 times 2. I lost track, but 2 to the 6th power. Okay, so what's going on here? Where do these come from? I'm basically coming up with different ways to write 64. And hopefully you're already screaming at the screen well, if we do that exact same thing with 16, there's two I can come up with good ways to write 16 using like a base and a power. I think 4 squared is 16, as well as 2 to the 4th power. So this is kind of a specific example, the 64 and the 16. But when I have a situation like this, if I can do it, this is going to make things a lot easier. I want to essentially rewrite this 64 and the 16 as something with the same base. So I actually have two choices here. I could do this with the 4 base, or I could do it with the 2 base. That doesn't always happen. A lot of times, there's only one option. So we'll just pick. Let's just say, you know what? Instead of doing 2 different ones, because it's going to work out the same way, let's use a 4 base. Okay, so see if you follow me on this one. All I'm doing on the left side of the equation is switching the 64 out with 4 to the 3rd power. Now I still need to take that to the x power, but I've just said, hey, get out of here 64. I'm going to replace you with 4 to the 3rd power because that's equivalent. On the right side, I'm going to do the exact same thing. I'm going to say, get out of here 16. I'm going to replace you with 4 squared because that's equivalent. And then we're going to take you to the x plus 1 power. So we're kind of working on, we're able to like manipulate it a little bit and initially not have the same base, but get the same base. I think that the trickiest or the hardest part about this one is when I go to simplify this first part, what should I be doing with these exponents right here and here? I should be multiplying. That's our power of powers property. So 4 to the 3 to the x power is equivalent to 4 to the 3x. That one's not a big deal. All right, hopefully one that we can all do. With the second one, when I go to multiply 2 times x plus 1, I got to make sure I'm multiplying that whole exponent. So there's like an implied parentheses there around that x plus 1 that I really need to like distribute this to. So on the right side, I end up with 4 to the 2x, not plus 1, but 2x plus 2. And it's going to make all the difference now. So we kind of end up where we were a second ago on the notes where it was 5 to some power is equal to 5 to some power. Well, these some powers have to be equal. And that's exactly where we're at. 4 to the some power equals 4 to the some power. I just need to make sure, again, I distribute there, but the finish is, okay, well, let's force 3x equal to 2x plus 2. Say, wow, that's it? Holy cow, let's subtract a 2x from both sides. X equals 2, and that's it. So it's kind of cool. I mean, it was a little bit of work, but the reward was essentially finishing with a relatively simple, like one-step equation solved. So we'll practice that, working on like kind of manipulating to get the same base. We could have did the exact same thing with 2's. I would have distributed the 4 here and here. I would have multiplied the 6 times x right here. So, all right, there's option kind of 1. Let's take a look here. Solve 6 to the x power equals 27. So now we're in kind of that second category of, well, I don't really have the ability to write 27 as a base of 6. Because 6 to the first is 6, 6 squared is 36. I can't change this base. It is what it is. And then same thing with the 6. I can't manipulate that and write it as something with there's no connection between this 6 and this 27, basically. Okay. I'm still going to give you some options on this one. I think the shorter option, and it seems almost like a little counterintuitive, but when I see something like this, 6 to some power equals 27, my first, let's split it. We'll kind of do method 1, method 2. I see this as let's rewrite this. Let's go from exponential form. Let's write it as a logarithm. So going back to that skill that we initially learned in 6.3, hopefully that's not too long ago, that we can still do it. That how would I just change this expression to a logarithm? So why would we want to go to logarithms? Just wait. I think you'll see it here in a second. All right. So the skill is the word log has to show up. The base of my power becomes the base of my logarithm. And then there's the weird kind of crossover thing. 6 to the x power equals 27. And then you're saying, well, why would I do that again? That doesn't help me. I don't know how to do logs. But if you think back in the previous lesson, the last thing we did was we learned a change of base formula that allows us to, hey, I can use that change of base formula to evaluate the log base 6 of 27 using common logs or natural logs, because my calculator has that ability. So I'm sitting right here and I think, you know what? I can do this. I'm going to switch to the common log and use just the log of 27 and divide that by the log of 6 and be done, basically. So let's see, log of 27. I need the calculator. I can't do it without. Divided by the log of 6. Here's what my calculator says. 1.839, 394. 8.8394. And before I just like move on, does this make sense? Right? Because we still did the mental component, the no calculator component, where it was 6 to what power is 27, right? We know it's going to be between 1 and 2. Hopefully we know that, right? 1 would put me at 6, 2 would put me at 36. It's a little closer to 2. So I like my answer. I think it makes sense. So option 2 is this, actually what the direction's saying to do, take the logarithm of both sides. Okay. So let's just say maybe we'll see it like this, and some people really latch on, Here's the original problem. 6 to the x power equals 27. So I see this here, and we'll either way, we'll use this skill where we take the log of both sides. So it doesn't hurt to kind of see it. So the first time probably ever for anybody that if you're watching this video is, all right, let's take the log of both sides. So I'm literally just going to, hey, all right, let's use the common log because that's one that I have the ability to evaluate. If we get the choice, it didn't say you have to pick a certain like log 6, log base 2, log base. We can pick whatever we want for a log and just say, hey, take it to the left side, take the right side of the log of the right side. And now you're like, what? I hate logs. You got 2 of them now. There's more of them. But here's the deal. What's the advantage to doing that? That's going to allow us, going back again to the previous section, it's lesson 6.5, these properties of having 6 to the x power says you can bring this x down out front. Hopefully we remember that. So as like a second step, I could write this as x times the log of 6 equals the log of 27. And the reason we did is now we're kind of all on one level playing field. There's no powers anymore. It's just x times the log of 6 equals the log of 27. And the log of 6 has a value. It's some number. So how would you move some number that's being multiplied by x in any equation that you're trying to solve? We would divide both sides by the log of 6, cancel here, leaving our x all by itself. And look at that. Look at the calculation. Log of 27 divided by log of 6. Where have I seen that before? Log of 27 divided by the log of 6. So I'm just going to write it because I did it once already without touching my calculator. Now, again, if this was the first time doing it, that you would obviously have to type that into your calculator and figure that out. But yeah, so the advantage is it gets unknowns out of the exponent. All right, let's look at one more. I think it's just kind of a level up here. It got an E base, makes things a little tougher. So jot it down. You can start it. You can try it. Pause it, obviously, and see where you can get. I'll walk you through the solution right now. So I would get rid of these numbers 6 and 8. They're just extra. We don't need them, right? So one at a time, move them. Whoops, that's not in the exponent. Equals 12. And then let's divide both sides by 6, right? That 6 isn't attached for life. We can get rid of that. Okay, so we made things definitely a lot smaller, a little simpler. But this E base, what's the deal here? I don't like it, So it's kind of like the last one. We could definitely take the common log of both sides and get this 0.25x out of the exponent. And we would be able to solve it. It's a little bit kind of tricky with plugging that into my calculator. But in the end, that's what the hangup would be is a key sequence on the calculator. I'm going to show you, and it's kind of specific to this case, but if we have the case, we might as well look at it. When E is my base as a power like this in an exponential function or an exponential equation, I'm trying to solve it. Instead of just taking the common log of both sides, this is a really good candidate. It's the perfect candidate to take the natural log still of both sides. I can't just do it to one side. Okay. Say, okay, I don't like that natural log thing, but I'll hear you out here. What's the advantage here? Well, if you recall back, lesson 6.23, when we did natural logs, we talked about inverses. In the natural log function and exponential functions with E as their base, right? I've got an E base on that natural log there. That inverse property says this cancels with this, just leaving us on the left side of this equation 0.25x. Okay, so we're digging deep a little bit there. That's one of those properties of inverse properties of inverses, but involving natural logs and E-base exponential functions. And then, it shrunk down pretty good here. And the last thing we would do is multiply both sides by 4, or I'm guessing actually probably most people are just going to divide by 0.25 and say, hey, x, again, we're going to have to round it, But if I said the natural log of 2 divided by just 0.25 or multiplied by 4, you should be getting hopefully about 2.7726. Okay. So a little bit, not necessarily a trick, but just kind of a strategic log to take at both sides. If you see an e-base, think, hey, at some point it's probably going to be a good idea to take the natural log of both sides. If this was any other base, we would take the common log. Okay? All right. So there's a couple different looks with exponential equations. That's half the lesson. The second half involves solving logarithmic equations. So we're doing okay. Hopefully you're following along. Let's do the same deal. Let's do a short note, and then we'll look at a couple examples, and we'll call it. So with logarithms, obviously, we got logs. It starts kind of the same way. If you've got logs on both sides of an equation, same base. Okay, so I'm kind of looking right here. I jumped right down here. If log base 2 of x is equal to log base 2 of 7, the only way that this statement could be true is if this thing right here equaled this thing right here. So, of course, x has to equal 7. So I look at these notes. They're almost the same as we did before. What if I give you log base 2 of x minus 10 and said that was equal to log base 2 of 2x minus 8, something like that. I don't know. I have no idea if that's going to work out, but the only way that this could possibly be true is if this thing right here was equal to this thing right here. So again, you kind of finish with a really nice x minus 10 equals 2x plus 8. That's awesome. Limited though, just like we saw with our first example before, it's limited. We're not always going to have that situation. There's not always logs on both sides of an equation. Sometimes there's additional numbers here that we're not going to be able to move. Okay, so we'll need some other skills, and specifically those skills are going to be changing forms, just like we did with exponentials, going from exponential to log. Well, sometimes it's going to be in our best interest to go from logs to exponentials. And also going back to the previous lesson, it's sometimes we're just going to have to condense logs down to a single log before we change form. So we'll see all three of these situations right here. We'll look at them. There's one just short note on what does it mean if we'll possibly have this situation where we have extraneous solutions like we saw before in another lesson. So we'll have to talk about what that looks like. All right, here we go. Let's do it. All right, solve a logarithmic equation. So I just on the surface, what am I looking at here? I've got log base 7 of 6x minus 16 equals log base 7 of x minus 1. We should be begging for problems like this. Why? It's a single log on both sides, log of 7, log base 7, both sides. There's no additional numbers over here, nothing in front. I literally just need to force this to be equal to this right here. How do I do that? I literally want to make 6x minus 16 equal to x minus 1. So we're in like pre-algebra territory right here. Now, again, I'm not trying to minimize it. That you need to understand kind of how logarithms work and what's going on there, but this is one that we can solve, right? Subtract an x from both sides. Add 16 to both sides. I'm not necessarily showing every single step here. We should be able to handle those. Add 16 to both sides. Divide both sides by 5 to get x equals 3. Sorry, forgot what I was doing for a second there. Now the check, if I plug that 3 back in, we should be checking pretty much any one of these. Log base 7. So here's my check. Log base 7, let's see, 3 goes in here. 6 times 3 is 18. 18 minus 16 is 2. I don't have to know what that is. I just need to see, okay, am I getting the same thing on the right side? So log base 7 of, let's see, 3 minus 1 is 2. Yeah, okay, we're good there. Right, that's identical. Those are equal. No matter what it comes out to, what the value of that is, I don't really care. That's x would have to equal 3 in this situation. All right, that's kind of the intro level or entry level. I guess they maybe both apply. All right, next one up. Level up here. All right, darn it. There's no more log over here. So I don't have that. I can't just say, hey, 3x minus 8 equals 2. Well, that's not true. All right, well, what's up here? We're getting a hint. Exponentiate each side of the equation? What does that mean? This is the part that I'm talking about with a single log. When we're down to a single log, I'm going to look to rewrite this. Just change your forms. This is kind of maybe the easier way to go. Let's see if we remember it. All right, so how does this work? 5, the base of my log becomes the base of my power. I do that weird crossover thing. So 5 to the second power is equal to whatever we're taking the log of, right? That's the definition of logarithm, basically. So, can I solve this? And I say, yeah, you better be able to, because this, again, we put ourselves, what's 5 squared? 25. Don't leave it as 5 squared. That might confuse the heck out of you. Do the 5 squared and say, wow, yeah, that's awesome. That's again, pre-algebra territory there, 2-step solve. Add 8 to both sides. Divide both sides by 3. And say, I like it. Now, this one's maybe a little bit tougher just to check. So if I plug this in, so here's my check, log base 5 of, let's see, 33 minus 8 is 25 equals 2. How do I know that that's true? I'm not super comfortable with logs. Like, I don't know. I could either do the rewrite portion and go, hey, 5 to the second power equals 25. You're actually probably better off trying to do the change of base formula and go log base 25, or log common log of 25 divided by the log of 5. It should come out to 2. Okay, so kind of 2 options for checking there. There's kind of a shorter, no calculator situation here. Just rewrite it. 5 to the second power equals 25. It's good in most situations, although we'll see here in a second, we might miss an extraneous situation. Or actually use the change of base formula. Okay, so that's kind of the check part of it. Look at this. I got one more example. Before we get there, how do we identify an extraneous solution with these log problems? Because we've never really seen, these are our first log equations we've ever seen. How do I know if one's doesn't work? So let's just say we'll solve one like this in a second, but for the sake of the problem, I've solved this. Holy cow, that looks crazy. And these are the 2 solutions I got, 10 and negative 5. How do I check this? Okay, so we're going to plug them in. If I plug in a 10 here, what happens? Log of, let's see, 10 times 2 is 20, plus log of 10 minus 5 is 5, equals 2. That's still kind of like, I don't really know. Is that true? Is that how that works out? And really what you'd be looking for at this point, like the dead giveaway that something's extraneous, is you're taking the log of a negative number. Log of negative 20 or log of negative 5. So let's just do the head-to-head right here. And I'm going to substitute in negative 5 now, and we'll see what happens. When I go to sub this in here, I get what? Log of negative 10 plus the log of negative 5. So I'm going right here. Negative 5 minus 5 is another negative 10 equals 2. So for just right now, I'm saying if I'm taking the log of a negative number, we're no good. Why though? That's just because Mr. Kroll says so? No. Well, yeah, but also no. Let's just focus on just that part of it. What does that actually mean? Log of negative 10. What does that mean? Why is this killing this problem here? Or why is that killing that solution and making it extraneous? Again, it kind of comes back to the rewrite here. What does this have a value of? Or what are we actually saying when we're saying log of negative 10? Well, what's the base? 10. Cross it over to some power equals negative 10. So I would challenge you to come up with a number that I could plug in here for x and say, hey, I'm going to take 10 to some power and get negative 10. So let's see. 10 to the first power is 10. Squared is 100. No, it ain't going to work. 10 to the 0 power. Well, that's 1. what about negative numbers? Well, that's still not going to work because 10 to the negative first power is just like 1 over 10. 10 to the negative second power is like 1 over 100. Oh, what about like a 1/2 power? Well, that's the square root of 10. That's not negative. The point is, it's impossible. That's not part of the domain. I cannot input a number and get a negative output with an exponential. Okay, so that's the kind of the why behind it here. So that's what you would be looking for when you're checking. Okay, I'm actually going to leave this right here, and we'll flip back to it because we got to figure out, like, okay, well, that's great. I guess I can probably identify now. Although even here, like, is my answer right? I don't know. We'll talk about here on our next example. But where do these numbers come from? Like, I got to figure out how I can do this. Okay, so that's kind of how we'll look. Basically, look for a log of a negative number, and that's a killer that says nope, done, extraneous. All right, last example. We'll do the whole thing. We'll solve it. We'll get some solutions. I'm guessing one of them is going to be extraneous. We got this built-in hint here, and then we'll talk about, well, okay, how do I know if my other answer is even right though? Okay. All right. So what's the deal here? It's not a simple solve because although I do have two logs, they're on the same side. They do have the same base, which is a good thing. We want the same base. But I can't move this log over here. There's this 2 hanging out. So this is like totally different from this first situation, right? Where it was, let me just clear it off there. Where it was same base, something, same base, something. We just set them equal to each other, right? Well, yeah. So hopefully we see that. And it's different from our second example is because this one only had a single log in it, just equal to a number. That one was kind of easy to exponentiate, to use that word. So what's the deal here? Here's our last option, I guess, when we're solving logs, for now at least, is this left side. I want to condense it. Make a single log. So going back to lesson 6.5, how do we do this? Well, if we can condense stuff as long as they have the same base, which we do, right? Base 10, common log, by multiplying the two things that we're taking logs of. So just like we did in the previous lesson, I'm going to write it for a second just so we can see, like, hey, we condensed this. We went from 2 logs to 1. But in order to do that, I need to multiply this thing times this whole thing right here. Okay. And actually, I want to do that multiplication. So let's multiply this out and say log of 5x squared minus 5x equals 2. Now, I think I probably want to keep this in parentheses just because I don't want to forget that's connected. Like, that's a product, this whole thing. It's not like this 5x is separate. That's all together. But at this point, we've actually kind of put ourselves back in this position. Let me clear it there. Where I've got a single log of something equal to a single number, like kind of a nice number, right? So we're at that spot where let's rewrite it. I can do it now because I know, hey, my base is 10. We just did this a second ago. 10 to that crossover power is equal to whatever we're taking the log of. 5x squared minus 5x. So logs disappear. I like that. No more logs. Can we solve this, though? And that was the part that, I don't know, we can get here. I kind of assume we can, but let's go through and do it. Let's do the 10 squared. That's 100 step by step. It goes 5x squared minus 5x. Don't start dividing by x's and stuff like that. Bring this 100 to the other side of the equation. Where's this going? So subtract 100 from both sides. 0 equals 5x squared minus 5x minus 100. Where are we at? This is a quadratic equation. We can solve this. We've done a ton of these this year. Now the 5s are definitely going to complicate things. This 5, this 100, but I'm also seeing these are all divisible by 5. Like, I can divide both, because it's an equation, as long as I divide this entire side by 5 and this side by 5. We're not breaking any rules. So no problem left side. 0 divided by 5 is 0. And then I essentially get cancellation on these first two. So x squared minus x, don't lose the minus, and then just make sure we do our 100 divided by 5, which is 20, so minus 20. So that maybe looks a little nicer. The numbers are smaller. Our leading coefficient's 1. How am I going to finish this? You know what I'm going to do? I'm going to factor it. What the heck is factoring? I totally forgot. I'm looking for two numbers that multiply to negative 20 that add up to negative 1. Oh, it's been a while. Not too long. We did actually, I think in the previous chapter, came up in kind of a, when we were solving equations before. But, all right, what's my combination? I've got, let's see, negative 5 times 4, negative 5 plus 4. Yeah, that works out. So this factors to x minus 5, x plus 4. And I know if we can get here, everybody knows the finish. All right, sweet. X equals 5, x equals negative 4. So we got two solutions. So now we're basically picking up right now where we did that practice checking for extraneous solutions. So I'm going to scroll it up. Obviously, I know you can pause. If I'm going too quick, you can slow it down and add that stuff. So 5 and negative 4. I'm probably going to actually clear some of this too because you should have probably seen, well, you should have seen all that. Here's the last part. What did we say? Oh, no. X equals 5 and negative 4. I know, kind of like the last section too that we saw extraneous solutions, a lot of times the negative value is the one that we take off the list, but we also did see a few where both were solutions and also ones where maybe both were non-solutions. So let's check it here, okay? Let's start with the 5. I'm at least confident. I feel better about the 5. So log of, let's see, 5 times 5 is 25 plus log of, we can do this part, 5 minus 1 is 4 equals 2. So far, like I like my answer because we said what was kind of the killer there? Negative numbers, log of negatives. We don't have that. How do I know if my answer is right? Like, is this actually the correct value? Here's where I would now try to condense this. Like we did before, but before, instead of it being 5x and x minus 1, now I actually have values there. How does this condense? Single log. Log of 25 times 4 is 100 equals 2. So now at this point, I could definitely, actually, I don't have to change bases because it was just a common log, although that's kind of just, I guess, coincidence. But I could go 10 to the second power equals 100. Sure. Yeah, I like that. I could use my calculator. What's the log of 100? It would say 2 because it's a common log. So there, I like 5. 5 is good. Let's keep that as part of our solution set. Last thing we got to do is just, I want to make sure everyone sees what does it look like when, kind of a number that we came up with is extraneous. So as it's going in, we're done, basically right off the bat. 5 times negative 4 is negative 20 plus log of, let's see, negative 4 minus 1 is negative 5 equals 2. So that was what I told you that, yeah, we're pretty much done at this point. There's a negative right there. Log of negative 20 doesn't exist. That doesn't mean anything. The part that I at least wanted us to see, and the reason we kind of came here is, well, how did this even happen? What's going to happen if I try to condense this? Or if I do condense it? Let's just say I didn't catch that and I say, hey, I'm going to condense this. Log of, what is negative 20 times negative 5? Whoa, positive 100. So whoa, what the heck happened there? No clue what's going on with that. But it was kind of this dramatic like moment I had going on there, and all of a sudden this little n showed up. Oh no. So not to get lost on that there, but right. So if I didn't catch that negative 20 times that negative 5 there, it's going to look at this stage right now. It looks like negative 4 is a solution. When I plugged it in and condensed, I got 10, my imaginary or my invisible, I shouldn't say imaginary, but my invisible base right here, 10 to the crossover second power equals 100. Well, yeah, heck yeah, that works. But this problem was dead before we got there. So that's kind of how we created it, by condensing like that. So yeah, I guess long story short, plug your numbers in, check, look for taking the logs of negative numbers. That's how you know you're extraneous. And then also take it off your solution set. I kind of did it without mentioning it. So a little sigh there. We did it. We got through it. 6.6. Yeah. So it's tale of two concepts: solving exponential, check; solving logarithmic, check. We're good. 6-6 is officially done. We'll call it there. I will see you in future lessons.